Okay, so we are picking up here with the equilibria in solutions of polyprotic acids. We left off the last section just looking at the percent dissociation in solutions of weak acids, and we were discussing weak acids. Now we want to look at polyprotic acid, something that's capable of donating more than one proton. And so there's just some trends that we want to discuss and sort of see. So we're going to start here with carbonic acid, or H2CO3, and this is reacting with water, and we see it undergo that first dissociation. And if we wanted to come up with an equilibrium constant for it, notice we have the acid dissociation constant Ka, but notice it has a 1 right next to it as we are talking about the first dissociation constant for this polyprotic acid. From there, we don't do much else just other than write the products over reactants as you're familiar with. And then so if we look at any sort of table in the back of a book, a chemistry book probably would work better than just any book. You're going to find that the acid dissociation constants is around 4.3 times 10 to the minus 7. So of course, being a polyprotic acid, we can do one more dissociation event. So what we can see here is that bicarbonate, HCO3 minus, can dissociate one more with one more proton and end up with H3O plus and CO3 2 minus. The equilibrium constant for that one is going to be written products over reactants just the same, and we end up with 5.6 times 10 to the minus 11. What you'll notice is that this is favoring the reactants more, and a lot more so than the first one. Carbonic acid is a weak acid in the first place. We end up 10 to the minus 7 there in the first one. But this is 10 to the minus 11, even favoring reactants even more. So it's even a weaker acid in this case. And one of the things that we have to understand that is when we have a polyprotic acid, it's always going to get weaker as we start dissociating more and more. The way that we can rationalize this is your proton leaving this this molecule, right? So in that first dissociation, when that first proton is dissociated, if you separate those two out, you have this proton, and then you have this HCO3 minus molecule that you're separating. These things have some affinity towards one another, obviously, because you've got a positive and you have a negative charge, okay? And so even there, you have something that water has to sort of intercede, break in there, and solvate that HCO3 minus to cleave it from that proton that's been pulled away. And so when we go to the next step, if we look at this, when you take that proton away from HCO3 minus, the bicarbonate, now you have the proton and it's leaving a 2 minus charge, that CO3 2 minus molecule. Now that's just, the attraction is obviously going to be greater when that plus charge is trying to be ripped away from a 2 minus charge. And that's what is going to always be the trend with polyprotic acids. As you start to deprotonate more, the proton has to leave a more highly negatively charged molecule behind, and that is very difficult to do because you're trying to separate that positive charge from that very negative charge. And so as a trend, we see the acidity decreases for the second hydrogen. And if we talked about something like phosphoric acid, which has 3 protons, is capable of donating 3 protons, then with each consequent removal of a proton, it becomes harder and harder and harder. And so therefore, these things become weaker and weaker acids. So here's just an example of some of the things I was mentioned. And so carbonic acid, we already discussed. Hydrogen sulfide is also capable of that. That smells like death and is pretty poisonous. 1 times 10 to the minus 7 for the first one, and then 10 to the minus 19. It barely wants to dissociate after that. Oxalic acid with H2C2O4 is 10 to the minus 2 the first one, and 10 to the minus 5 for the second one. And as I mentioned, phosphoric acid, 10 to the minus 3 for the first one. It's not that bad of an acid. And then the second one, though, goes down to 10 to the minus 8. And for the third, 10 to the minus 13. So like I said, consequently, it just gets smaller and smaller. And sulfuric acid, that's a strong acid. So we just have even a very large there that you can bother quantifying. It's probably up in the 10 to the 30s or something like that. Ka2, though, is only 10 to the minus 2. So once it loses that first one, it doesn't have a great propensity to lose the second proton and become SO4 2 minus. So if we're looking at sort of doing some calculations here for these solutions, we'll take a look at first just looking at carbonic acid. We're going to start with 0.020 molar of it, so a modest amount molarity of it. And you're given both the Ka1 and the Ka2 here, okay? So we're going to first figure out what the amount of dissociation we get from that first step here, that first dissociation. And so we set up the reaction. You see it's in equilibrium. And then, of course, we probably want to use an ice diagram. So I set up the ice diagram. I plug everything in there. As you'd suspect, everything's got a coefficient of 1, so nothing fancy with the x's there. We didn't start with anything on the right, so we know we are moving to the right. And so we start out with that step. Then what we can do is we can go ahead and set up our Ka1, and then that ends up with x squared over 0.020 minus x. You'll also notice I took the liberty of making our approximation here. 10 to the minus 7 is pretty small as its equilibrium constant. And so with that, I know it's probably very little dissociation from what we initially started with. And so I suspect that our approximation is going to be pretty good. So I just set it to x squared over 0.02. And then solving for that more simplified equation, we end up with 9.3 times 10 to the minus 5 molar. That subsequently gives me the bicarbonate concentration of 9.3 times 10 to the minus 5 because it's equal to x, and the hydronium concentration of 9.3 times 10 to the minus 5. The carbonic acid concentration, if I do 0.02 minus that 9.3 times 10 to the minus 5 within our sig figs, it's still going to end up at 0.02. And the pH there, of course, you're just doing minus log of that concentration of the hydronium ion, and that gives me 4.03. If we want to check if our approximation's good, remember you're just basically taking the amount dissociated divided by the amount that we started with, and that's effectively the percent dissociation, and we check and make sure that is under 5%. And if we look at what we get for this, 9.3 times 10 to the minus 5 divided by 0.02 and multiplied by 100 gives me 0.5%. And so this is a pretty good estimate, and we're good to go there. So now, one thing that we want to realize is that basically we only got 10 to the minus 5 molar of hydronium ions from the dissociation, this first dissociation. So we should suspect that the second dissociation is going to lead to even less dissociation. So for this, it's pretty accurate to say that we're not going to get much more hydronium ion from that HCO3 minus. It's not going to dissociate a great deal further from that. And so we can almost lock down that concentration of HCO3 minus, and we can lock down the concentration of the H3O plus because they're not going to change very much. It's not dissociating much further. And so what we can do is that's going to simplify our step for the second equilibrium to find the carbonate concentration that we might be after. So I set up the equilibrium equation here for HCO3 minus, and I'm going to go ahead and set up my value for Ka2, which is just H3O plus times the carbonate over the bicarbonate concentration. Now we said that the H3O plus and the HCO3 minus, because the subsequent dissociation is so small, it's 10 to the minus 11 is what our equilibrium constant is, that we should suspect that the H3O plus concentration, the HCO3 minus concentration will remain unchanged. That makes my calculation a lot simpler. So through a little algebra, I can basically solve for the carbonate concentration. And then I know that the carbonate concentration is the same as the hydronium concentration as we had solved in the first part of this problem. Those will cancel out, and that will give me that the carbonate concentration is effectively the same value as Ka2, which is 5.6 times 10 to the minus 11 molar. Okay, so in this slide, we want to take a look at the equilibrium of a strong polyprotic acid. And so we're going to take a look at H2SO4. we know that since H2SO4 is a strong polyprotic acid, what we're going to end up with, and upon its first dissociation, if you had 3 moles of H2SO4, you would have ended up with 3 moles of HSO4 minus and 3 moles of H3O plus as it dissociates completely. And so this problem wants us to investigate the pH of a 0.1 molar H2SO4 solution, and it gives us the Ka2 value of 1.2 times 10 to the minus 2 at 25 degrees Celsius. So what we're going to want to do is we're going to want to set up the equilibrium equation for that second dissociation, and so we end up with HSO4 minus reacting with water to form SO4 minus and the hydronium ion. Set up our ice diagram, and as I said before, if we started with 0.1 molar of H2SO4, we know it completely dissociates into the HSO4 minus and the H3O plus. So we can presume that we're going to start with 0.1 molar of those two species. And so that's our initial concentrations. And notice we have 0 moles of SO4 minus. Given that, we know the reaction has to proceed to the right. And so in the following row, we end up with a minus X for the HSO4 minus, and on the product side, we end up with 2 X's for each of those, or an X for each of them. And then summing those two entries up above, we end up with 0.1 minus X for HSO4 minus. We end up with X for SO4 minus and 0.1 plus X for H3O plus. And there, just as I said, we know that concentration because we know the dissociation is complete for that first step. So we set up our equilibrium constant, and then we subsequently go ahead and plug in our values of X. And then with a little algebra, I can go ahead and just rearrange this and eventually get it into a form that's suitable for the quadratic formula. Plugging all those values in, I end up with a X value of 9.8 times 10 to the minus 3 molar. And if I go ahead then and plug in what our values are for the HSO4 minus, we end up with 9 times 10 to the minus 2 molar by just doing 0.1 minus that 9.8 times 10 to the minus 3. If we add it to the 0.1, or sorry, I should say for the SO4 minus, it's just X, so it is 9.8 times 10 to the minus 3 molar. And for the hydronium, it's just the 0.1 plus that small value of 9.8 times 10 to the minus 3, yielding us 0.11 molar. If we go ahead and determine what the pH is for this problem, we're going to get 0.96. So that's what we get for the expected pH if we were to go through this in a very thorough fashion. However, you'll note that they didn't get much dissociation from that second that second dissociation. We didn't get much additional H3O plus. So if we just were to calculate what the pH was just from looking at the first event, saying that we have 0.1 molar of H2SO4, so it created 0.1 molar of H3O plus, and that's all we looked at, we calculated the pH, we would have got a pH of 1. So you can see that this is not really a big difference. So in most of these solutions, unless you're looking for really good accuracy or the problem specifies, you're probably good just doing a quick calculation with just the one dissociation of that strong acid, as the second one is not going to add much to it. But if you were looking for the sulfate concentration or something like that, then it's instructive to go through this. If we're looking for the equilibrium that we're getting with a base, and so looking at these weak bases, the generic formula that we can write for it is we can say that B reacts with water. It acquires a proton, becoming BH+, leaving that water as hydroxide. And so the equilibrium constant in general can be written as just BH+ times the hydroxide divided by the concentration of B. And that is the, so again, here's another one of these times you're seeing a subscript on a K. This is the base dissociation constant. Before we were looking at Ka's, which was the acid dissociation constant. So yet another little equilibrium constant that we're throwing in there that is relevant to bases. If we go ahead and look at a few bases there, we have ammonia, Notice nitrogens are all over the place. Nitrogens are very common as weak bases in biological systems and all kinds of different things that we see. So ammonia, aniline, dimethylamine, hydrazine, hydroxylamine, methylamine, all those good things are all bases. And then you can see the Kas that we have there for their conjugate acids as well. So we want to tackle how we calculate the pH and the equilibrium concentrations of a solution that has a weak base present. So what we're going to look at is a solution of 0.4 molar ammonia, which has a 1.8 times 10 to the minus 5 base dissociation constant at 25 degrees Celsius, and it specifically asks us to calculate the pH. So we want to first set up our equation, and so it's just ammonia reacting with water to form NH4 plus, that ammonium ion, and the hydroxide ion as well. Okay. We set up our ice diagram here, and we know that we start with 0.4 molar of NH3. We have 0 molar of NH4 plus or hydroxide. We know the reaction's proceeding to the right, so we ended up with a minus X for NH3 for its change, plus X for NH4 plus, as well as for hydroxide. Summing those, we end up with 0.4 minus X for NH3, and then we get X's under the NH4 plus and the hydroxide. Setting up our base dissociation constant, we just end up with products over reactants, and then we can plug in our values for equilibrium there, and we end up with X squared over 0.4 minus X. We can make a pretty good assumption here that the 0.4 is going to remain relatively unchanged, and so we just do X squared over 0.4 to simplify our problem. Solving for X just then becomes the square root of 0.4 times Kb, and that gives us 2.7 times 10 to the minus 3 molar. We can check if that is a good approximation by doing that X value over our initial value, and we end up with 2.7 times 10 to the minus 3 molar over 0.4. Multiply it by 100, we end up with 0.67%. This is well under 5%, and so this approximation is quite good. Plugging in our values for X into NH4 plus and hydroxide yields the same thing of 2.7 times 10 to the minus 3 molar. We want to get at the hydronium, or we want to get at the pH, which requires the hydronium ion concentration, but we only have the hydroxide. So bear in mind what we have to do is then we have to use our relationship between the hydronium and the hydroxide to figure out what the hydronium ion concentration is. So that's just Kw over the hydroxide concentration, and that yields 3.7 times 10 to the minus 12 molar. We plug that into our pH equals minus log of the hydronium ion concentration, and we end up with 11.42. So here's a clicker question. You'll see as we progress along, sometimes I'm not going to include as many of the steps just because I know you're getting a little bit more familiar with things, and so I'm going off of that assumption when I perhaps skip a few steps, and there's a limited space to write on this particular slide. So in this case, we're dealing with dimethylamine. It's a weak base. It's got this Kb value of 5.4 times 10 to the minus 4. And we have this very concentrated solution of 1.5 molar. We know our approximation is going to work if it's that concentrated. And so it asks, what's the pH of this solution? So I'm going to go ahead and start off with the Kb value, and I didn't include the ice diagram here. I just start out with the Kb, and notice here a lot of times with these bigger molecules it's better to just call it base as in B, and its protonated form is BH plus, and that makes things a little bit simpler to write. So I just write BH plus times hydroxide over B, and that is effectively the reaction that we're looking at. If I were to set up an ice diagram, I would have ended up with X squared over 1.5 minus X. And like I said, we can make our approximation with good accuracy here, so it ends up with X squared over 1.5. And we end up with X value equaling 2.8 times 10 to the minus 2 molar for the hydroxide concentration. And so if I go ahead and do that, 2.8 times 10 to the minus 2 over 1.5 times 100, we end up with 1.9%. Again, safely below that threshold of 5%. And so this approximation is pretty good. It's asking for the pH though, and we have the hydroxide concentration. So what equation do we need now in order to figure out the pH? We need the hydronium ion concentration. So we weren't going to use that relationship we used in the last problem. It's just Kw over the hydroxide, and that gives me 3.6 times 10 to the minus 13 molar. Plug that into my pH, I end up with 12.45, which is solidly right there at A. So A is the answer to this particular question. So one of the important things is all problems you're going to be given Ka or Kb for a particular acid-base pair. And so we want to know what the relationship is between them. And so we'll use NH4 as an example here. And so here's the acid for in the pair of NH3 and NH4. So this is NH4 plus reacting with water, and it's donating its proton, producing H3O plus and NH3. So this is a Ka value for this particular problem. If we go ahead and look at the opposite for NH3 reacting with water and being in equilibrium, it's picking up a proton, so that's the base, and we end up with NH4 plus and hydroxide. It's given a Kb there. We can tell that these cancel out, and so what that leaves us with is just two waters reacting to form hydronium and hydroxide. So we can get a relationship of that. Remember that you can multiply the equilibrium constants when you're summing reactions. And so if we sum the reactions, that's the same as saying that Ka times Kb equals Kw. And we can see that in the math there as well. I put the Ka formula and the Kb formula in there, and we can see that those things cancel out, and it leaves you just with the hydronium times the hydroxide. So those things are in fact equal to one another. But this becomes a very useful equation for us. We can verify its accuracy by go ahead and taking these values that we can find in the back of the book, the 5.6 times 10 to the minus 10 and the 1.8 times 10 to the minus 5, and we can multiply them. We get 1 times 10 to the minus 14. So these things do give us the same, the value of Kw that we would expect. But more importantly, mostly in a great deal of problems, you're just given a Ka or Kb, and sometimes you need one or the other. We can switch back and forth between these by just relating them with that Kw value there. So a little algebra, and we can solve. Another consequence of that is we can also say that taking the negative log of the left and right side, knowing that, and when you do negative log of 10 to the minus 14, you'll end up with 14. And if you take the negative log of that left-hand side, you'll end up with pKa plus pKb. And so those things have to sum to 14, so that can be quite a useful expression for us to use at times as well. So let's take this problem of piperidine. This is an amine, and it's what gives you that spiciness in black pepper, actually. It's not capsaicin in this case. And so piperidine has a Kb value of 1.3 times 10 to the minus 3. It asks us to calculate the Ka value for its conjugate acid. And so, of course, all we have to do then is it's very similar to how we did that hydroxide hydronium and switch back and forth. We just do Ka equals Kw over Kb, and we end up with 7.7 times 10 to the minus 12. So it's just as easy as that to figure out what the other conjugate acid or bases, Ka or Kb, is by just using this relationship here. If we wanted to, we could also establish what its pKa is, because this is so much fun. And so we do minus log of 7.7 times 10 to the minus 12. We yield 11.11. If we wanted to, if we were so inclined, we could figure out what pKb is, because we just can basically do 14 minus that 11.11, and I end up with 2.89. And if I was so inclined, I can see that I can get back to the Kb value that I started with by doing 10 to the minus 2.89. And a little bit of round off error gives me 1.29 times 10 to the minus 3. I think that's good enough to call about the same as the value that we started with. So there's just a little maneuvering with those values there. So just looking at the acid-base properties of salt, and when we have a solution of these acids or these weak bases, what are the pHs that they yield? And so we know salts can act as acids or bases, and we want to determine when we're mixing these acids and bases, what kind of solution are we going to be left behind. So if I mixed a strong acid and a strong base, we can expect that we're going to get a neutral solution. If I end up with mixing a strong acid and a weak base, we get an acidic solution, and we mix a strong base and a weak acid, we get a basic solution. We'll discuss all these in a little bit more detail going through the next couple of slides. We're going to start here discussing strong acids and strong bases. So these always yield neutral solutions. And if you remember, the conjugate acid of a strong base or the conjugate base of a strong acid are always considered to be incredibly weak acids or bases. So much so that we can consider those to not actually interact with water if they are the conjugate pair of some strong acid or strong base. So effectively, these ions that are mixed with strong acids or strong bases have no activity with water. They don't produce H plus ions, they don't accept H plus ions, they don't produce hydroxide. They are completely sort of inert in the water. And so we look at some examples of that, and cations that we can take note of are things like lithium, sodium, potassium, magnesium, calcium, strontium, barium. Anions being chloride, bromide, nitrate, perchlorate, and all those do nothing with water once they're reacted, and so they don't contribute to the pH in one way or the other. And so we expect, once we've neutralized all the H plus and the hydroxide to form water, we're just going to end up with a solution with a pH of 7. If we go ahead and look at a strong acid plus a weak base, we expect an acidic solution. So why is that? If we go ahead and take an example of NH3 with HCl, then when the HCl fully neutralizes that NH3, we're only left with NH4 plus. The chloride doesn't behave as a strong acid or a weak acid or weak base. It doesn't really have any activity at all. And so all we're left with really that has activity as far as being an acid or base is the NH4 plus at the end of the reaction. And so what we can expect is that since we have a one weak acid present, that NH4 plus is subsequently going to react with water in equilibrium to form NH3 and hydronium ion. And so we can expect that we would have a slightly acidic solution at the conclusion of a neutralization of a strong acid with a weak base. When we go ahead and look at a strong base with a weak acid, we end up with a basic solution. It's very similar to the reasoning we just had for the other problem. So if I took hydrogen cyanide, a weak acid, and reacted with the sodium hydroxide, I end up with sodium cyanide plus water. That cyanide ion is the only thing there that's present that's going to act to contribute to our acidity or basicity. In this case, cyanide is going to act as a weak base. And so if we only have cyanide present, which is a weak base, we expect it to react further with water in equilibrium to give us HCN and hydroxide. And so now you should have a solution that's slightly basic as a result of that. So one of the next questions we might have is, how are we going to deal with this if we have a solution, if we have acidic cations and basic anions that are both present in a salt? So say we had ammonium carbonate, for instance, which is composed of an acidic cation and a basic anion. And so these are both weak acids, weak bases. And so how can we tell if this is going to yield acidic or a basic solution? How can we figure that out? So the way that we're going to do that is we're going to compare their Kas and their Kb values. If the Ka value for the acid is stronger than the Kb value for the base, then the solution is going to yield an acidic solution. If the Kb, however, is stronger than the Ka or larger than the Ka, then we expect the solution to be basic. And if those two are the same, then we expect the solution to be approximately neutral. So if we look at our example here, we have a Ka of 5.6 times 10 to the minus 10 for ammonium, and we have a Kb for carbonate that is 1.8 times 10 to the minus 4. And so what do we think this is going to yield? Which one is bigger there? Well, if we look at it, the Kb should be greater, and so we expect a basic solution. Just looking at another example of what we discussed here, we have cations from strong base and strong acid, and we end up with ions that react with water as none, and so we get a pH of solution that's just 7. Once we have cations from the weak base anion and a strong acid, we're seeing a bunch of things that are weak acids that are left behind, and we end up with a pH that's less than 7. If we have these other ones, these are just another form of weak acids that we have present. We end up with less than 7 for that third row there. And the fourth one, we have weak bases present after we react those, and so we end up with a pH that's greater than 7. And when we're talking about weak acid or weak base, it's always just a comparison of the two. So that brings us to our last topic, which I only have one slide for here, and it is the most general form that we discuss acids and bases. It's a bit more sophisticated, and it's something that you focus definitely a lot more on in organic and inorganic chemistries, is using this Lewis acid or base definition. And it's just a broader definition for acid-base chemistry. It doesn't require that we're in an aqueous solution, and it provides a good context for understanding how reactions occur sometimes. So if we're looking at a Lewis acid, the way that we're going to define it in this world is that a Lewis acid is just a lone pair acceptor. A Lewis base is going to be a lone pair donor. And so if you look at the subsequent examples there, like for this one in aluminum, we have an aluminum cation that's going to accept a pair of electrons, and we're going to consider this a Lewis acid. And the water is the one that is donating its electrons for that bond, and so that is considered our Lewis base. If we look at copper, then copper is the one that is accepting that Lewis pair, or that lone pair from the ammonia, and so that is why it's considered a Lewis acid, and ammonia is the one donating it. That's why it's considered a Lewis base. And this is also the reason that most ammonias, or not ammonias, but I should say a lot of nitrogens are weak bases, is because they have an extra lone pair that sits on top. Maybe you remember from when we did so many of those Lewis diagrams in the first semester. So it has that lone pair on top, so it's always able to donate those, or is often able to donate those, and that means it can act as a Lewis base. And the last example there, we have that sulfur trioxide reacting with water, and in this case the sulfur is accepting that lone pair from the water, and so we consider that to be our Lewis acid and the water to be the Lewis base in that instance. So that's all we got for this chapter.